What's up, everybody? Welcome to Earth Science. So the Rock Cycle Lab. The idea is going to be that what you've got to do is only tell me if the rock is metamorphic, sedimentary, or igneous. It's not like the other ones where you have to get specific and say that this igneous rock is granite, whereas this one's pumice, or this metamorphic rock is gneiss, and this one's schist. You've got to only put them in the three categories, which may make it sound easier compared to the other ones. And maybe it is, but also there's a bit of a trick to it. We really got to recognize the idea that these three rocks form in different environments and therefore have different characteristics. So, when I walk around the room, what are those characteristics? I don't know if I can switch cameras here to show you the room. Probably more shenanigans than it's worth. But in the room right now, there's 30 rocks at all of the desks, and that's going to be the job when it's time for that lab. Grab your laptop, walk around to each one of them, visit them, and try to figure out which rock is which and why. So to begin, a good idea is to say, what are the three environments where we form these three different kinds of rocks? Keep in mind the whole time, this is kind of printed. I guess you can blow it up, right? You're on a computer, but it's kind of printed too small to be practical. It's also sitting right on pages, 6 and 7 of your reference tables with all of the rock stuff. So take a peek there, and it will always tell you how these three rocks formed. In terms of the environments, let's go through them, starting over here with a brighter color. Magma. And I say starting kind of as where I'm arbitrarily choosing to start because it's a cycle. These things all can transform to each other over and over and over again. When magma works its way towards the surface for different tectonic reasons that we'll get into in tectonics in Reckon Period 4, either way, it's going to work its way towards the surface and it's going to cool. And the type of rock we get because of that, cooled magma or lava, is igneous rock. Maybe it's a good idea to remember that those two types, the type that form inside the earth, are intrusive, and the types that form up on the surface are extrusive. Cooling faster because they hit the atmosphere, cooling slower because they're insulated by the planet. That's all important stuff, but I guess not so much for the Rock Cycle Lab. I just want to throw it out there as review. For the Rock Cycle Lab, all we got to really know is that igneous rocks form from lava or magma, and then add to that what things do I look for in that rock that are assigned to me that it is indeed an igneous rock. And that's what we'll do up here on the sheet. But first, let's say that every single bit of exposed bedrock on Earth is being attacked by the atmosphere and all those processes that we talked about, surface processes. So weathering is on a daily basis and a nightly basis beating the crap out of Earth's bedrock. And when it beats it up and breaks it into pieces, it creates sediments. And those sediments get caught in wind or in moving water like streams and rivers, and they get transported, which we call erosion. And then they make it to places where the conditions are more stable, usually underwater, not always. Where they get dropped back off, we call it deposition. So that deposition happens in layer upon layer upon layer upon layer, over and over and over again, until the lower layers have so much overriding them that the particles are getting squished closer together. The water is getting squeezed out of it, leaving behind a mineral cement as that happens, and forming probably the easiest rock to remember because it's made from sediments. It is called sedimentary rock. It didn't turn purple. Hopefully review, as was the igneous, but again, where we'll take this today is what things do I look for in sedimentary, like in a rock, to let me know that it is sedimentary. But first, this diagram isn't really to scale. That doesn't help. But if we can draw a little arrow here to say with a break, to say that way down there, deep within the Earth's crust, not so deep that it gets so hot that it melts, but a pretty good distance down at depth. When you go down, down, down there, you get enough heat and pressure that you distort the minerals. Whoops. get all smashed up. And we call those our third and final rock type, metamorphic. Rocks that change due to that tremendous heat and pressure without melting. Otherwise, they go back and they're igneous. All right. Those are the three. Let's make this one big, because why not? All right. So that's going to be the job. And it may still seem a little elusive. Don't worry. We'll talk about it right now. When I go pick up a rock, how do I know it's igneous? You guys picked up skills on doing the light colored versus dark colored and the coarse versus fine to say, oh, this is andesite or rhyolite or basalt or gabbro or whatever, right? But how, stepping back from that, do I pick up a rock and just say, this is igneous and here's the reason? This is sedimentary and here's the reason? Because that's what you got to do. When you get to the lab 30 times, you're going to say, check, this rock is sedimentary. Here's my reasoning why. This rock is igneous. Here's my reasoning why. So let's give kind of like all the things that I'll put on there. I tend to put only rocks that are going to be stand out in some way, right? I could be mean and do the really subtle rocks that, man, is it this or is it this? It's close. No, I'm going to do ones that have very obvious characteristics. So basically, what are those characteristics? Let's start easy with igneous. I don't know. I'll put a star because this is what I drew on the board when we did this in class. What if it's vesicular? Now we got to know what that means, but don't panic because you know you have a reference table at all times. And rather than saying what it means, there it is right there. Vesicular means that it has gas pockets in it. Those are pretty easy to spot for students. It looks like Swiss cheese. It's got little tiny holes from gas. So yeah, we can write it here. You won't have to actually write gas pockets, but you see them? Boom. That's igneous. There's no way sediments form that. And under metamorphic pressure, there's going to be no gas pockets surviving in a rock. So when I see gas pockets, it's a no-brainer. I'm done. I don't have to think anymore. This is an igneous rock. And that's all the job is. Like in the igneous lab, you would have had to have then say if it's pumice or scoria or whatever it might be. Here, boom, vesicular is igneous. Same with another pretty easy one, glassy. Obsidian that a lot of people recognize from that lab. The only way that that's going to form is if it's igneous. So that one will be very easy. Some of these will be hard. Don't worry. But there's a couple that are really easy with giveaways that are nice for you, right? So here's a harder one. It has uniform interlocking crystals. I'm going to try to jam that in this box here. Uniform interlocking crystals. So what the heck does that mean? Let me actually grab a rock to explain this one. So here's one that exhibits that. Each one of these crystals in this igneous rock, we talked about this, when it was a magma, these were getting bigger, like a molecule at a time, at a very slow pace, getting bigger and bigger and bigger and bigger. When did they stop getting bigger? Well, when they run out of space, because the other crystals next to them are also simultaneously getting bigger and bigger and bigger and bigger as this whole entire thing cools. So each one grows and grows and grows and grows until it hits other ones that are also growing, which means occasionally, often, they're going to like intertwine and interlock with each other. The only way that that's going to happen is if this like grew together in that kind of natural pattern. Like, and the example I always use is, if you wanted to say that this was sedimentary, you'd say, hey, Mr. Ruff, I see bits in there, and those bits look like they were stuck together. And I see your points, but what I'm going to argue the difference is that they fit together too perfectly. If you wanted to argue this was sedimentary, I can see two, I don't know if it shows up on camera or not, but they fit together so perfectly, you'd have to argue that that bit formed, and then weathered, and then eroded, and then got deposited, and happened to land right next to another bit that also went through that weathering, erosion, and deposition, but had a little notch that was just the right size to get this one in there. And then that had to happen, hundreds of thousands of times in this sample alone, let alone all the rock in the world. It's not likely. You're not going to have that situation where they all fit together that perfectly unless they grew together. This shows me that they grew together out of that liquid magma. Otherwise, you'd have to say, it'd be like saying, Uh, I took a 1,000 piece puzzle and I chucked it down the stairs and came together. They all just fit together perfectly, randomly. It's not going to happen, right? It's not going to happen over and over and over and over again anyway. So to get them to all interlock perfectly like puzzle pieces, they have to grow together out of that magma. Yeah. To draw that, what I'm going to do, I'm going to say, I'm going to ask you to do this if you can. I'm just going to randomly chuck a bunch of crystal shapes just by drawing little jagged weird shapes. They're not flattened in any direction. They're just kind of randomly without any pattern like that. But they interlock just right. In fact, you could say down here that these fit together like puzzle pieces. See that? You got to say igneous. These are not individual sediments that got stuck together and they all happen to be exactly the right shape. They grew together from that magma. They're igneous. Have I said that enough? Hopefully. So those will be the three that you'll look for as you do those 30 rocks. Best of luck. Next, sedimentary. Let's start with an easy one again. Very easy one. Fossils. Fossils are a result of animals that died in the right conditions where they were buried in sediment, which guess what? Makes sedimentary. It's the only way you get a fossil. If an animal jumps into a volcano, you're not going to get any tangible results from that in the rock. If a rock with fossils, this was a question in the metamorphic, by the way. If a rock with fossils went through metamorphism, that's enough heat and pressure to completely mangle the minerals in a rock. It's also going to completely mangle any fossils that are in the rock. So fossils, the only way you're seeding it is sedimentary, because that animal got buried in sediments. It's that easy. Not bad. If you see that one, easy peasy. What about cemented particles? And if you're saying, well, that looks like cemented particles, like I get you, and that's going to be where the subtle parts of this that are difficult. You'll have to really look and see, do they fit together, interlocking, or does it look like a bunch of separate bits kind of mushed together? You'll have to try to get there. That's the hard part, but I'll be here to help. And what if I see like layers of sediments? Some kind of layering present in the rock. You see, and this is what I usually do for the drawing. Layer, 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 like that. Because of the way that like sedimentary accumulates. Sediment gets deposited, then more sediment gets deposited, then more sediment gets deposited, then more sediment gets deposited in layers. So those layers get preserved in layered sedimentary rock. Can you spot that? Look for those three. Those are your sedimentary. Then it gets a little harder. I think the easiest one to spot here is banding. You did a pretty good job with that. The class swoop in general did a pretty good job with that yesterday in the metamorphic lab. The rock that had the fairly bold stripes. And again, hey, this kind of looks like that too. I know that's what's the hard part, but we're going to practice and practice and practice and get better at it. So those bold stripes, in fact, you would automatically know that that's nice because of what we did yesterday. And again, what you did a great job with. What if we see you could use foliation? I see the minerals in alignment as a reaction to that heat and pressure. That'll pop up. Banding is a type of foliation, so you could answer foliation for both, but hey, let's be specific and say I see banding. You could probably also just say what foliation is, which is mineral alignments. And that only happens in reaction to the heat and pressure, so that's that. So I draw that kind of similarly to the layers one, only saying that because of the heat and pressure, they tend to be a little bit more beat up and intertwined with each other. And the important part, the hard part, is to see that the bits that make this up are all kind of flattened along those foliations. That's what makes it different than layers of sediment, layers of rounder sediments that pile and pile and pile and pile on top of each other. That's the hardest bit. If you can do the difference between layers and foliation, the rest of this you're going to whip right through. And I'll be here to help. We can work on it. We'll see how you do. Sound good, folks? All right. We'll see you soon for the lab. So long for now.